I started the recording. So today we are going to talk about how we do texture mapping in OpenGL, and I'm going to show you an example program in which we apply three different textures on three different models using the programmable shaders. And also we are going to talk about how we can implement shadows in OpenGL with the help of programmable shaders. And some existing programs I already shared with you actually contains a lot of helper functions to implement one of those techniques, which is shadow mapping. For example, depth as texture, the jumping spheres where we see the Z buffer mapped as a texture. That shows you how you can get the depth buffer of some scene from some angle, from some camera, as a texture image. And the shadow mapping algorithm uses those depth values to determine whether an object is in shadow or not. And we are going to see how it does that. Okay, so I think it's a really nice technique. It's a really nice idea, which was developed, proposed in 1970s, 80s, maybe. I'm not sure, but there were no programmable shaders when shadow mapping was first proposed. So it was probably very difficult to implement and time-consuming back then, and therefore many games did not have this. They had baked textures, pre-computed textures for shadows usually, but with the help of programmable shaders, it's possible to have real-time dynamic shadows with these techniques. So we are going to learn about those two. So depth as texture, for example, is one example. The terrain example that I shared with you also uses the depth map actually, and it uses the inverse of some, I think it's like the inverse of shadow. The terrain visibility, where we have a camera placed in the scene, which is in a different location than the camera that we are looking at the terrain. And our goal is, for example, to mark the places where terrain is seen by that second camera. So shadow is something like that actually. It's like a shadow mapping application. If that camera was the light source, the parts that the light source sees will be the parts of the terrain that are not in shadow. What is shadow basically? A shadow is places where the light does not reach. The light source does not have a direct line of sight. That's what shadow is, right? So the green parts in that terrain visibility would be parts that are in shadow. If it was that camera was some kind of a light source. Okay, if it's a directional light source like that, or spotlight, because the camera has a certain field of view angle. If it's a point light source in all the directions, if you have a light source like this, you have to, modeling it with a camera would be difficult. You have to rotate it, get lots of angles. But if you know that your light source sees the entire scene from some angle, the parts that the light source does not have line of sight will be the parts that are going to be in shadow. So actually both of those example programs, depth as texture and terrain visibility, implements the shadow mapping techniques. It doesn't create shadows, but it uses the same helper functions that are used in shadow mapping to do some other things, right? So we are going to see those today, and my plan is to finish this texture mapping in OpenGL and the shadow mapping. And there's also another technique, shadow volumes. I'm not going to show you an implementation of that. That's another algorithm for implementing shadows in OpenGL. It's a little bit, I mean, it's also used, but I haven't implemented that one myself. I implemented shadow mapping, but the shadow volumes technique, it's a really separate, different algorithm than shadow mapping, and we're also going to talk about that. And my plan is to finish these things today, and next week we are going to talk about how to model curves and surfaces that are smooth but not non-polygonal objects that have certain curves, like for example a cloth, a curtain, or some sand dunes, which are curved, and they're, how do you model that at infinite resolution? By using mathematical functions, basically polynomials. We'll be using third-degree polynomials and splice them together, merge them together in some way to create these curved objects in computer graphics. That's going to be the topic of next and last week. All right. So we talked about how so this is like API reference. I told you on the slide we see how the necessary functions to set up texture mapping in OpenGL. So just like creating a programmable shader, we have integer identifiers for two things. The texture is texture mapping. The texture image itself and the sampling methodology is decoupled from each other by having these two concepts. A sampler is this methodology that samples, gets colors from a texture image, and the texture image is the actual image, a two-dimensional, or maybe a two-dimensional texture, one-dimensional, three-dimensional textures. So there are different types of textures, but the most commonly used one is a two-dimensional texture image, as we have seen in the first part of this course as well. So these are this is how it's decoupled, and as I said, these are the OpenGL setup functions, and I'm going to show them directly from the example code. But we set certain parameters of our sampler, whether we use nearest filter, linear, bilinear interpolation, or whether how we treat when UV values, texture map values are out of bounds. For example, do you repeat the texture if you want to tile some area? If you want to do tiling, you may want to repeat the texture. But if you may have different textures in which you may want to just repeat the last column or the last row. So how we do the texture wrapping when UV values are out of bounds, those are the parameters we usually do to set. We set our sampler, and there may be different active textures. Usually, if you're just using single texture mapping, which means that you're mapping a single image to a single object. Sometimes we may blend textures. We may have an airplane image texture, and we may have a separate image which is like the texture image of rusting, a rust, or maybe a shadow, a pre-computed shadow, maybe a separate texture. So if you want to combine different textures on the same model, this is also called multi-texturing. You may have multiple textures, different texture units that you access at the same time. But if you're doing single texturing, you usually just use the texture unit 0 to do that. So we are going to talk about all these things. And GL text image 2D is like in vertex buffer objects. It's the function that copies the texture image onto the GPU. So when we call this function, this image 1D array, which has a pointer to where the image is located in CPU or in memory, is copied onto the GPU with this function call. As I said, there may be different texture units. Samplers are attached to those. And we also need, just like we provide normal vectors to our vertices, we also provide the texture coordinate attribute. Again, just like vertex array objects where we send the vertex pointer or normal pointer. There is also another function which says the texture coordinates for these vertices are here. And again, in the core profile of OpenGL, which is the newest version, which on OpenGL in embedded systems, for example, all these functions are deprecated. They're not used. Instead of saying them textures, normals, or vertex coordinates, they just, all of them becomes attributes of a vertex. And it's the programmer's responsibility to tell this attribute should be used as UV coordinates. This attribute should be used as vertex coordinates. We directly access those attributes, multiply them with MVP, and assign it to an output vertex coordinate or an output texture coordinate to set up these things. But using the previous version of this programmable shader is also good with these built-in variables. Everything is easy to use, so we can use this function to say that these are the texture coordinates for my vertices. And then in the programmable shader, we can access the texture coordinates by using built-in variables. They will be automatically interpolated for fragments, and in our fragment shader, we can use the texture 2D sampling function, which gets a sampler. So all these parameters, whether this texture 2D is going to use the nearest pixel or bilinear interpolation to get the color, all this information is in this my sampler. So my sampler is like a package that contains all these parameters about sampling, whether to use bilinear, whether to use nearest, how to wrap the texture, clamp to edge, or repeat the texture. These things are here in this my sampler parameter package. And texture 2D gets them together from the sampler attributes and automatically samples from our active texture, currently active texture image, whatever it is in the GPU memory, and gets this UV coordinates as floating point values between 0 and 1, or maybe more than 1 if it's out of bounds. Again, it knows how to sample it, and it returns a color. So what we do with this color is really our responsibility. We can use it as diffuse reflectance coefficient. We can use it to blend it with some other constant color. We can directly assign that color to the output frag color. And this is how the texture image is going to appear on the surface of the mesh of our model. Okay, so you can send different samplers. As I said, you can either blend or do different things. And also, this sometimes when the texture image we're applying is applied to a smaller, the fragment sizes. If the fragment sizes are smaller than the texture image itself, which means that multiple fragments may map to the same pixel. So sometimes we may need to minify our texture, or sometimes we may need to magnify. Okay, if for example we are trying to map a very small texture to a very large area, if there are lots of fragments, how do we do magnification? How we do minification? These are, again, we need to do some interpolation in that cases, because there is no one-to-one mapping between a fragment and a texture image if their resolutions are different, their sizes are. I mean, when I say resolution, it's the projected resolution of an mesh triangle, because if you view a triangle from far away, a single triangle with potentially infinite many fragments, a single triangle may occupy only 1 or 2 or 3 fragments if it's very far away. Those fragments are your pixels, and how you get a 500 by 500 image, how you minify it to a single text as a couple of fragments is this is your minification filter. And magnification filter is when you have a small texture, 500 by 500, but imagine you're viewing a very large triangle from close up, from very close distance, and in that case you'll either see some blurring, and in order to minimize this blurring, or in order to minimize the square looking of texture pixels, you may use bilinear interpolation for magnification, but for minification, just pick the nearest one, may be the good thing to do. So this is called how when we minimize the texture or minify or magnify the texture, what we do. There's also a concept called MIP mapping, and OpenGL creates different MIP maps for ourselves, which means that for the same texture, we may have the same different resolutions of the texture applied in different settings. I may have a lower resolution texture, a very high resolution texture, and based on whether I'm mapping it to a small triangle, I mean a triangle very far away or a triangle very close, I can use the smaller size or the larger size. And this can be done automatically by OpenGL if you set up your MIP mapping. There are functions for that. I haven't used it myself, or maybe it's automatic that I just call a function to use it, but I didn't do anything substantial to do the MIP mapping myself. So when the texture image and the polygon are roughly the same size, we directly map it. But what happens when the texture is smaller than the area? Then we need to magnify the texture. The other thing is, texture is larger, the mesh polygon is smaller, then we need to minify the texture. And so this minification and magnification we can do. For example, what will we do if we try to map this texture with lots of pixels in a row to a rectangle that is going to be displayed, which occupies one fragment per in a column. Okay, I mean a column of fragments, but in a single column there is one fragment. So how are we going to which one of these colors I'm going to assign this to this one? Is it the average? Which one? So this is really it may be difficult. So different aliasing effects will occur. So we need to use either nearest pixel or bilinear interpolation to do that. And here are some examples. Actually, these may be videos or maybe they are figures. Let me just see whether, yeah. These are just pictures, so we can also see them here in their original sizes. So aliasing, anti-alias results. So you can do some blurring, to get the corners not shown correctly. If you look at this picture closely, some of the edges, you're going to see zigzags. In order to reduce those zigzags, you can do anti-aliasing to remove that. Okay, so I'm not going to spend too much time on these texture details, high frequency, low frequency, and MIP mapping. It's done automatically by OpenGL. We are not going to talk about algorithms or techniques to do these things. They're really more in the area of more image processing. As I said, OpenGL supports MIP mapping. There's a function which allows you to create custom filtering for each different levels of your MIP map. And yeah, this one, look at this. There's a single function which says GL generate MIP map, and it will create different levels of resolution textures automatically for you. All right, and now we come to frame buffer objects. So this is actually here, we're done with texture mapping, but let me show you the example program and how we do that. So I'm going to share this Marty and Rux program, which maps 3 different textures. So if I click on these textures, this is the rock texture. It's like this. Looks like a nice rock texture. And I have a mold texture. Okay, like looks like grass or mold, or yeah, it's just some mold on rocks. You can also map this moldish texture on tree trunks. You may have trees their north faces of trees, for example, may be mapped with this texture, or and this is the Marty texture. So here are three textures. Well, this doesn't look like a zebra image to me at all, but because it's just unwrapped, we are going to map this 2D image on a three-dimensional model, and different parts of this texture image is going to be mapped to different vertex coordinates that have three-dimensional coordinates. For example, a single eye image, since the face is symmetric, we can use the same image to map it to left and right eye by changing the UV coordinates in such a way that this is going to be mapped correctly on both and left parts. Also, the toes, they are also symmetric. The back legs, front legs, they are symmetric. So a single image is enough for that. Also, the left body and right body, they are probably different. Symmetry is used a lot to reuse this part of the texture and map it to different vertices. So as you can see, there is no one-to-one mapping here. Certain parts of the texture may never be mapped. They may just remain empty. There may be no UV coordinates that map any vertex to this region. And there may be more than one vertex that map to the same UV coordinate. All right, so we just it's like just wrapping some kind of texture mapping. Really is wrapping like a 2D folded paper folded on top of some three-dimensional object. Now, how do we do this? Let's see the code. So yeah, so I'm going to share this with you. I'm just going to show you the important functions here. Yeah, this is vertex. So normals of the vectors, probably I don't need them because I don't have any lighting computation. I just do texture mapping. So there are some unnecessary function that I don't use. Probably I just stripped the light computation parts from the shader, but we are going to see what we do. Reading shader, loading shader, they're just standard things that are also in other programs. Yeah, here's this function that I want to show you. Load texture ASCII. This one just gets a file name, a PPM file. So if you're using a PNG or JPEG texture, you need to have the necessary libpng or libjpeg function calls to read your image into the memory. So this one is a really simple PPM format that we're familiar with from our ray tracing assignments. Look at this PPM. It's ASCII. It's a 592 by 592 image, and these are the RGB values of our texture. So this is the Marty texture, which is just a bunch of integers, as you can see. All right, so this program just reads them. It reads the header and reads the width, height, maximum intensity, and reads all of these RGB values and fills an image array, okay, as a single one-dimensional array. Okay, so this image is like RGB values are just one after another, RGB, RGB, RGB. So this is how we read into our image array, which is of pixel format. Pixel is just a struct here that contains 3 values. Where is my pixel? Pixel, somewhere here. Yeah, right here. Actually, yeah, pixel is not a struct at all. It's an array by itself. So three values, okay, of bytes from 0 to 255. They're unsigned bytes. So a pixel is just an array of unsigned bytes with of size 3. Now let's get back to this one. So I haven't basically this is nothing but an unsigned byte array of 3 times the width height. So instead of doing this, I could directly have said width times height times 3 times size of unsigned int. Okay, it's nothing more than that. So this is exactly how I fill the array. And here are the functions, the OpenGL functions that we have seen on the slides to set up the texture parameters. So I don't actually use the sampler here. I just generated texture. I think it's possible to just, instead of decoupling the sampler from the texture, we can have a texture object coupled with the sampler. So in this example, in this source code, for example, we don't see any generate samplers. Okay, we don't have a sampler here. We just say generate a texture. GL bind texture means that my current texture that is active, because all these functions that I'm calling here is modifying, again, since there is no object orientation here, these parameters are going to modify the current active texture. Okay, so just like we bind a buffer, GL bind buffer, this is GL bind texture makes this current texture the active texture, and we set the sampling parameters. And here is the function that we copy the texture image data to the GPU. Okay, so we copy it onto the GPU, and then we bind texture 0, which is nothing. So therefore, whether we have a side effect, if we are using some other texture functions outside this function, therefore we reset the current active texture to 0. And after we copy our image, the texture image in memory can be freed, just like our vertex information and normal information. So this is how we load a texture into OpenGL onto the GPU. So let's see what I do in the main function. So where do I have the... So I have a vertex buffer. I send the vertex information to the GPU, normal information, texture coordinate buffer. Now I have an additional texture coordinate buffer, and index buffer are the triangle indices. So these three, which are not uncommented, were what you used in assignment 3. Okay, now if you want to add textures to your assignment 3, you may use an additional texture coordinate buffer, and we get the necessary storage space from our CPU. We fill in our normal data, vertex data, and texture data. The texture coordinates are read from these vertices information. Probably I read, when I read input, that read input gets the vertex data, normal data also, I think. Yeah, somehow it's computed somewhere. And the texture information is also, we get them. Then this is the place where we initialize our vertex buffer objects. We send the vertex data to GPU. We send the normal data to the GPU. We send the texture coordinate data to the GPU. And that's it. And all these memory that I allocated for vertex, index, normal, texture data can be now freed from the CPU, from the memory. Everything is safely copied onto the GPU side. I read my shaders, I enable my client state vertex array is enabled, normal array is enabled. Now an additional thing, the texture coordinate array, I enable that one because now in addition to the normal, in addition to the vertex coordinate, I now have a texture coordinate. If you see this code, for example, the only difference is that we just had added a new attribute, texture coordinates, instead of the normal vector. In addition to the normal vectors, we also have a texture coordinate, just like another attribute. We enable texturing, texture 2D is enable depth test, and we load 3 textures. So this load texture ASCII that we have seen above loads the textures, create OpenGL texture objects, and assign the integer texture ID to this multi-texture, to these 3 variables. So I load these 3 different PPMs. I send all of them to the GPU. I copy all of them. I create different texture IDs for all of them and assign the unsigned integer handles to these three variables. I also send my model view projection matrix to my shader, and then this is setting up. Again, I use the linmath library to set up perspective, view, the model, projection, all these matrices. Resizing of the viewport. If I change the width and height, if the window is resized, I do that. So before drawing things, I bind them and tell OpenGL that this is where my normal is in this vertex buffer object. My texture values are in this vertex buffer object. So I also tell OpenGL by setting up these pointers, I tell OpenGL where my data is in the GPU. These pointers, as you can see, they're all zero. They're all null because currently they're not referring to some memory. This normal pointer, if you're using vertex array objects, this pointer, the last parameter of this, supposed to show some memory location on CPU. It's zero, it's null. Why? Because we are currently using a buffer on the GPU, and when you say GL bind buffer, whatever buffer we created earlier, its unsigned integer ID is going to tell us that. So this is the actively bound buffer on the GPU, and your normal data, normal coordinates are in this buffer. So this is how we point it to that. Texture coordinate is just something that is added, and we draw the three objects separately, and that's it. This is the end of the whole file. So each object is drawn separately. As you can see, we translate Marty to a different location. Actually, they're all placed in the same location. Maybe, I'm not sure. So this is this is drawing Marty. So these are the transformations that I apply to the Marty object. For example, if I don't rotate that, let's see what will happen. Yeah, I'm just going to copy this one, and let's go to, okay, when I say render, okay, as you can see, Marty is nicely looking straight at us. It's not rotating, and there are two rocks that are rotating around it. Okay, so these are the transformations that we apply to them. So we may also have things like this. So if, for example, this rock is actually scaled. So when you build a scene, a world scene, usually when you have different models downloaded separately, the world scene is not constructed nicely. Sometimes, for example, the rock may actually be very large. And if you may want to scale it down to build your own environment, they may be rotated differently. So in order to have these things, you apply different modeling transformations to your objects, and this is what we do. And here, when drawing these things, as you can see, we set the texture map for each one of them. There's a texture map variable in our shader, and the active texture is all zero here, as you can see. So how do I make, if all of them is texture zero, how do I know whether I'm going to map the Marty texture to this model or the rock texture to this model? It's this, the GL bind texture function in OpenGL. When you say GL bind texture, GL texture to the Marty texture map, and you GL active texture, GL texture 0, just say that the unsigned integer texture ID that I generated earlier, let's make it the active texture. Let's make it the texture unit 0. So in all of them, we are using texture unit 0 because I'm not doing multi-texturing. I don't need to assign different texture units to these different texture. They are all texture unit 0. Okay. The only thing I change from model to model is here this function which tells which texture to use to bind. Is it the multi-texture, rug texture, or for example, let's see what will happen if I do rug texture here, rug texture map. Okay, there's a question. That's a good question. For these modeling transformations, there's no generic algorithm for that. Actually, there is something called in different when there was Java 3D, for example, like maybe 20 years ago. There is a data structure which builds the entire scene as a scene object where you may have geometry, you may attach transformation nodes to geometries, and it's really object oriented. Oh, the UV coordinates of the vertices. Let me just first I answer Bugra's question. So there are actually data structures which allow you to create a scene with these attached transformation objects to these to the geometry, and you can reuse transformations. So you can really the whole scene really is a hierarchy. At the leaf nodes, you may have the geometry itself, and then you may combine different geometries into groups of geometries, and you can assign transformation nodes to them. And at the top, transformation nodes may have another transformation node. So rendering an object will be like traversing in this scene hierarchy from root node to the leaf node. And as you're traversing the tree, you apply each transformation you encounter. So you can actually have such a scene graph. It was called scene graph. You can have a scene graph structure because it's not necessarily a tree, because since you share geometry, multiple branches may point to the same leaf node. That's possible. So it's not from computer science perspective, it's not going to be a tree. So it's called scene graph. So there are some techniques like that to build data structures to make these transformations of objects easier. Now I hope this answered your question, Bugra. Now the UV coordinates. The UV coordinates are actually inside the model file. So here are my vertices, my vertex coordinates. And where are my UV? Yeah, these are the UV coordinates. Okay, so they're in the model, and the place where we read and assign them is here. Let me get back to here. When we read the scene, so here we read our file, the input file. Yeah, read input. So this read input function gets this geometry and texture coordinate information. And the normal vectors, I think, were not in that file. But let's see when we read this input. Where is this read input? Let me just, yeah, this is read input. Yeah, it reads the number of, this is the number of vertices. These are the UV coordinates. So the UV coordinates are read into ST. So we have a mesh kind of a vertex information. So this, if you look at the vertex struct, where is the vertex struct? Yeah, here. We have a vertex struct which contains vector position, normal, and ST coordinates, which are the texture coordinates. So we read them directly from the file. Okay, so we read them from the file, and now how do we assign them to vertices? We just use the vertex buffer object. We just say, this is my texture, so this is where we load them inside here. Yeah. So this is how we send that texture data. The texture data is first, we just use the S and T coordinates of that vertex struct. We fill in an array of T data, just a one-dimensional array, ST values. And then this T data is our texture coordinates. They are going to be matched one by one with the vertices when we say this. This is the place where we send this entire texture information and saying that these are going to be my texture information. It's going to be a total number of vertices times 2. Send this data to the GPU. Actually, at this point, the GPU does not know that, whether this data is texture or normal or something else. So we just copy the entire array. So this command just copies the entire array to the GPU, not knowing what we are going to use it for. We just know that we're going to use it for some static drawing, but whether it's going to be vertex, normal, texture, at this point, the GPU doesn't know that. The place where GPU knows that these are texture coordinates is this. This is the function call in which we say that, okay, this is the place where we say to the GPU, you know that place I copied to you earlier on the GPU, the vertex buffer, the buffer object on the GPU where we call t-chord buffer. Now let's talk about that. This is exactly what this GL buffer says. So, and then this function tells the GPU, okay, this data that I copied earlier, these are the texture coordinates. So this function tells that those data is going to be texture coordinate, and it's going to be used 2 by 2. Every two values in that array are going to be used as texture coordinates. So, and that's it. We just after that, it just works like magic. Let me just also show you the texture, the shader code, the vertex shader, and the fragment shader. They are actually very short, as you can see. If you look at the vertex shader for doing texture mapping, all I need is to define a varying texture coordinate, which I want to be interpolated per fragment. So, and that variable is nicely in my multi-text chord 0 built-in variable. That's a good question, Bugra. Yeah, we may actually contain maybe a single buffer containing all of those vertices normal, so as in an interleaved manner, and we can create. That's another alternative. It could be done instead of having all these different. I don't know how inefficient it's to switch from one buffer to another, working on the same buffer. I think it may be. It may be more efficient to have all of them together, because when you're going to, if for a vertex, if you're going to access all of its attributes, you want them to be close by in memory, right? There may be some small inefficiency when the GPU is getting this data in all these different buffers. I think it may be, what you're saying may be right. I mean, having all of that data attribute by attribute, all vertex attributes bundled together in one after another on the same vertex buffer object may be more efficient. Okay, but yeah, you need to be. It's maybe more in terms of programmer's side. You need to be more careful about how all those strides, how many bytes you need to jump to get the next vertex information, but all you need to do is do some simple mathematics, compute that size of bytes, and tell GPU that the next vertex information is this many bytes after. Yeah, it's actually, it does matter, I think. Yeah, what you're suggesting may be more efficient than having separate buffers, but I really don't know. It really depends on the GPU architecture. Maybe GPU is really efficient. Maybe if you just keep them separate, having the same normal pointer pointing on the same location may have other things that may be more efficient. I'm not sure. We should really, it really depends on the architecture of the GPU. Now, what I do here interesting, as you can see in this texture coordinate that is varying, is I set its x and y coordinate as differently, because I think in my PPM image, the UV coordinates are upside down in terms of the y coordinate. So the y coordinate inversion is, I need to do this here. We can see what will happen if I don't do that. And this is my normal vertex, which I don't use the normal actually. This normal could be used if you're going to do some lighting computations. You can add it here. But since I just wanted to show you simple texture mapping, all I do here is get this texture coordinate as varying, the gel position is get, and the normal vector is not even multiplied. It's not even transformed. It may be wrong here, so we may need to do some additional things with the normal vector here. And so texture coordinate is going to be automatically interpolated for fragments within our triangles. And then we have the sampler 2D texture map. This texture map that we send from the program render.c. If you remember, this is our sampler. This is the texture map that we sent, and we sent the value 0. So actually, the texture map that is used here is just 0. The active textures ID, which is just 0. But just even in that case, we just we should define it as a sampler 2D object, and these are its. We use that texture map. The texture coordinate is the interpolated texture coordinate. We use the built-in function to sample a color from that texture image, and we just set it the resulting color. It's this simple, okay? And when we run it, let me compile it again, and we see a different Marty this time with rock face. This may be rock face Marty. Look at this. Now it's actually a statue. Now we have the Marty statue. Instead of the zebra texture, we may have this nice rock texture mapped onto Marty. All I did was change the texture image from Marty texture map here to rock texture map. Okay, Marty texture map. Let's get our Marty back here. Now, when I say render, we get Marty back. And let's get this rock back to its original size. Now, what I want to show you is that if, let me compile it now and render. So this was how it originally looked like. All right. Now, if I change anything again in the vertex shader, for example, if I don't do this 1 - if I don't invert my texture coordinates, let's see what happens. And I don't need to compile, as you can see. Wow, Marty looks really strange. Okay, so if you see there's something wrong with your textures, with those UV coordinates, probably you may need to invert, because the image coordinates, they may start at 0 at the top, and in some modeling programs. Okay, if for example, if this Marty was created in a program in which the texture coordinates were started, the 0 coordinates started at the top, and if we use our UV coordinates in OpenGL as if they're starting from bottom, if OpenGL uses that, then we need to invert our texture coordinate to have this. This is just inversion of the texture coordinate, and I run it again without any compilation, and it works correctly. Yeah, we can map multiple textures simultaneously on a single object, and we can average them. Exactly, we can do that. So multiple textures can be mapped. So in that case, we will have different samplers, different multiple active textures, texture unit 0, texture unit 1, texture unit 2. We can bind different different texture images to each of them on the CPU side, and we can have multiple samplers, saying that sampler 0 is sampling from texture unit 0, the other is sampling from texture unit 1, the other is texture unit 3. We can get 3 different colors from them and blend them in any way we like in the fragment shader. So multiple texturing is possible. We can even combine it with the computed light. We can use diffuse, ambient, specular. We can also combine the texture color with those. We can use some of them as a shadow map. A shadow map can be a texture which we may use to determine, for example, we can use a shadow texture map, and based on the color we get, we may have an if statement saying that if shadow texture at that position, if its red color of that shadow map is 1.0, then just add the ambient color otherwise add the ambient, diffuse, and specular color. So we can actually have a shadow map that we as a texture map on this. The shadow mapping algorithm is something entirely different. If we have it as a fixed, constant shadow map as a texture map that we read from an image, the disadvantage of that is that those shadows are going to be static. They're not going to be dynamic. As objects move or as light sources move around, your texture map is going to stay at its place. But it may be a good idea to, if you have a scene in which light sources and some objects around them are static and they cast static shadows, you can pre-compute those shadows as texture maps and then use texture mapping to do these things. Okay, so this concludes the texture mapping in OpenGL. Let's have a 10-minute break, and after the break I'm going to talk about those frame buffer objects quickly, and we will directly jump to the shadow algorithms, shadow volume and shadow mapping algorithm. And I'm going to share the Marty and Rux program, the entire program with the textures and the model on Auth2 class after the lecture today. All right, let's have a 10-minute break now, and after let's meet at 10:40 and we'll continue with shadows.